Hello everyone. In the previous class I have explained solution of differential equation, that too particularly solution of a homogeneous differential equation. In today's class I am going to explain solution of non-homogeneous differential equation using inverse differential operator method. So let us consider a general differential equation of second order to explain. So a naught d square y by dx square plus a1 dy by dx plus a2 y is equal to phi of x. As I already explained in the previous class, if the differential equation contains phi of x equal to 0, if phi of x is equal to 0 in the given differential equation, then the equation is called homogeneous differential equation. If it is not equal to 0, then the equation is called non-homogeneous differential equation. And the solution of a differential equation contains two parts, that is yc plus yp, where yc is called complementary function and yp is called particular integral. And for homogeneous differential equation, since the value of phi of x is equal to 0, the value of yp is equal to 0. No need to find the value of particular integral. There we have to find only the complementary function, which I already explained in the previous class. So now I am going to explain how to find a particular integral. For homogeneous differential equation, we have to find just the complementary function, just yc only. In particular integral, we have to find both yc and yp. To find yc, we have to consider the LHS part of the equation. To find particular integral, we have to use RHS part of the equation, that is the given function of x. In a non-homogeneous differential equation, we have three types of function. Type 1, if phi of x is equal to e to the power of ax, that is an exponential term. Type 1 function is phi of x is an exponential function. Type 2, if phi of x is a trigonometric function, particularly sin ax or cos ax. And the last type, that is type 3, if phi of x is a polynomial. Phi of x is a polynomial. These are the three types of phi of x function in non-homogeneous differential equation. And the value of the particular integral is based on the nature of the given phi of x, whether it may be an exponential function or a trigonometric function or a polynomial. Based on the nature of the phi of x, we have to find the particular integral, that is yp value. On combining the complementary function, that is solution of the LHS part, and yp value, we get the complete solution of the given differential equation. So next I am going to explain how to find particular integral if phi of x is an exponential function. Type 1, phi of x is equal to e to the power of x. If it is an exponential term with a constant term a x, x is the variable here, a is the constant term. To find the value of yp, so if phi of x is equal to e power x, then the equation is in the form of a naught d square y by dx square plus a1 dy by dx plus a2y is equal to e to the power of ax. So then this equation can be written as a naught d square plus a1 into d plus a2 of y is equal to e to the power of ax, where this a naught d square a1 d plus a2, this d is called a differential operator. So this is a differential operator equation. From this equation we have to write the auxiliary equation. Before writing the auxiliary equation, this equation can be written as f of d of y is equal to e to the power of ax. To write the complementary function, First we have to write the auxiliary equation of this differential operator equation. Then using that auxiliary equation we have to find the roots of the equation. After getting the root we have to write complementary function. So now to write a particular integral of this equation, we have to write a differential operator equation as f of d of y. So f of d is called function of a differential operator where y is the variable here is equal to e power of ax. Then the first step to find the value of particular integral is e to the power of ax divided by f of d. That is, we have to divide the given function e power of ax by function of the differential operator. We have to divide e power ax by f of d. After that we have to replace that differential operator element d to the element a, where this a represent the power of exponential term. We have to replace this d by a. After replacing d by a, we get f of a here. This f of d becomes f of a. Then after replacing d by a, then we get f of a here. If f of a is not equal to 0, if f of a is not equal to 0, then this obtained result not equal to 0, that obtained result is called, then yp is the particular integral. Then yp is the particular integral if this term, that is denominator term, is not equal to 0. Suppose if f of a is equal to 0, on replacing d by a, if we get the denominator term as 0, then we have to continue further. If it is not equal to 0, then the obtained result will be the particular integral. Suppose if it is equal to 0, then we have to continue. Then the second step is, so this is the first step. Then the second step is, after getting this denominator term equal to 0, then we have to write yp is equal to, what we have here, e to the power of ax divided by, in the previous step we have f of d. If we get 0, while writing the next step, we have to differentiate this denominator with respect to d. So that is f dash of d. We have to differentiate the denominator and we have to multiply the variable x here. In the first step, e power ax by f of t. On replacing d by a, if we get it is not equal to 0, then that is the final solution. If it is equal to 0, then we have to continue further by multiplying x to the numerator and differentiating the denominator. After this step, again we have to carry the same procedure. Replace d by a. The next step, again replace d by a. On replacing d by a, what we get? F dash of a. So we get f dash of a. Again, if f dash of a is not equal to 0, if this term on replacing d by a is not equal to 0, then yp is the particular integral. Suppose if it is equal to 0, if f dash of a equal to 0, then we have to continue further. That is, again yp is equal to, what we have here, x e power of ax. If we get again 0, then we have to differentiate the denominator one more time. Here we have f dash of d. On differentiating one more time, we get f double dash of d, and in the numerator we have x. On differentiating one more time, here we have to take x square. So in the first step, e power x into e power ax divided by f of d. If it is equal to 0, then we have to multiply x to the numerator and differentiate the denominator term. Again replace d by a. If it is not equal to 0, then that is the complete solution. Otherwise, if it is equal to 0, then we have to continue the same procedure by multiplying x to the numerator and differentiating the denominator. Again we have to replace d by a. Replace d by a. Again we have to carry the same procedure. If it is not equal to 0, then that is the final solution. If it is equal to 0, then we have to continue by multiplying x to the numerator and differentiating the denominator one more time. So this is and etc. Again if we continue, we have to continue the same procedure till we get non-zero element in the denominator. So this is the procedure to solve a non-homogeneous differential equation with the phi of x value e power of ax. First problem on type 1 is 6d square y by dx square plus 17 dy by dx plus 12y is equal to e to the power of minus x. Under type 1 we may expect functions of the form phi of x is equal to a constant term e power of ax, a to the power of x, and hyperbolic functions like sine hyperbolic ax and cos hyperbolic ax. Under type 1, that is under e to the power of ax category, we may expect functions in this form. If it is a constant term, we have to write that in the form k into e to the power of 0x. K is the constant term here, we have to substitute a is equal to 0. Second one, e power x, that is regular exponential term. Next one, a to the power of x. If the given function is a power x, we have to write in the exponential form as e to the power of log a into x. E to the power of log a into x. And for hyperbolic function, sine hyperbolic function is equal to e power ax minus e power of minus x ax divided by 2. For cos hyperbolic function, e power ax plus e power of minus x divided by 2. These are the expected functions under the type 1 e to the power of ax. First problem is 6 d square y by dx square 17 dy by dx plus 12y is equal to e to the power of minus x, where a is equal to minus 1. So this is a complete non-homogeneous differential equation. To find the solution of this one, we have to find both complementary function and particular integral. So first let us find complementary function by taking the LHS part of the equation. So the given equation can be written in differential operator form as 6d square plus 17d plus 12 of y is equal to e to the power of minus x. So this is the differential operator equation. This can be written as f of d of y is equal to e power of minus x. So let us take this as equation number 1 and this one as equation number 2. We will use this result while finding particular integral. So now to find complementary function, write the auxiliary equation by replacing d by m in equation number 1. So auxiliary equation is 6m square plus 17m plus 12 equal to 0. So by replacing d by m, a constant term, we get a quadratic equation in the form 6m square plus 17m plus 12 equal to 0. So we have to factorize this. Here the coefficients are 6, 17 and 12. So the factors are, on multiplying 6 and 12 we get 72. Now we have to select two factors such that on multiplying we have to get 72 and adding or subtracting we have to get 17. So here the factors are 8 and 9. 8 into 9 is equal to 72. 8 plus 9 is equal to 17. So factorizing this, 6m square plus 8m plus 9m plus 12 equal to 0. On simplifying this, in these two elements, common term is 2m. 6 and 8 we have common element as 2m. On taking 2m as common term, remaining element is 3m square plus 3m plus 4. On taking 2m as a common term, we get 3m plus 4. In the next two elements, common term is 3. On taking 3 as common term, we get 3m plus 4. Again the common element is 3m plus 4, 3m plus 4. Taking 3m plus 4 as common, remaining element is 2m plus 3. 3m plus 4 into 2m plus 3 is equal to 0. Then equating to 0, 3m plus 4 equal to 0. 2m plus 3 equal to 0. Then m is equal to minus 4 by 3 and m is equal to minus 3 divided by 2. So therefore the roots are minus 4 by 3 and minus 3 by 2. So the roots of the given equation is minus 4 by 3 and minus 3 by 2, which are in case 1 category, that is real and distinct root. The obtained roots are real and distinct. For real and distinct, the complementary function, that is yc is equal to c1 e to the power of, since we have two roots, we have to select two complementary elements c1 and c2. c1 into e power of minus 4 by 3 into x plus c2 e to the power of minus 3x by 2. Solution of complementary function is c1 e power of minus 4x by 3 plus c2 e power of minus 3x by 2. So that completes the first part to finding the complementary function. Next, to find particular integral, that is based on the nature of the phi of x function, that is RHS function. Next, to find yp. To find particular integral yp, so we have to use the procedure. Here e power of minus x is the phi of x function and f of d is equal to 6d square plus 17d plus 12. For that, let yp is equal to e to the power of minus x, that is the given function, divided by f of d. E power of minus x divided by f of d. E power of minus x divided by, where the value of f of d is equal to 6d square plus 17d plus 12. That is the value of f of d. What is the first step? First step, we have to replace d by a. What is the value of a here? A is equal to minus 1. Then yp is equal to e to the power of minus x whole divided by 6 into, on replacing d by minus 1, we get minus 1 whole square plus 17 into minus 1 plus 12. Simplifying this, e power of minus x divided by minus 1 whole square is plus 1 into 6 minus 17 plus 12. On simplifying this, 12 plus 6, 18. 18 minus 17, we get 1. yp is equal to e power of minus x divided by 1. Here the denominator value is not equal to 0. If this is not equal to 0, then this is the solution of particular integral. If it is equal to 0, we have to continue further. but since this is not equal to 0, this is the solution of particular integral. Therefore, the solution is y is equal to yc plus yp. Y is equal to, what is yc? c1 e power of minus 4x by 3 plus c2 e power of minus 3x by 2 plus, and yp value is e to the power of minus x. This is the complete solution of the given differential equation, complementary function plus particular integral. The second problem, solve d cube minus d square plus 4d minus 4 of y is equal to sine hyperbolic 2x. Sine hyperbolic 2x can be written in the exponential form, so it comes under type 1 category. First, finding the complementary function. Here the given solution is already in the form of differential operator. So given that d cube minus d square plus 4d minus 4 of y equal to sine hyperbolic 2x. This sine hyperbolic 2x can be written as e to the power of 2x minus e to the power of minus 2x divided by 2. That means here we have two exponential element. One is e power of 2x by 2 minus e to the power of minus 2x divided by 2. So finding the complementary function for this, let us write auxiliary equation. Auxiliary equation is m cube minus m square plus 4m minus 4 equal to 0. So here this is the equation of degree 3, m cube minus m square plus 4m minus 4 equal to 0. To find the root, either we have to apply synthetic division by finding one of the root using inspection method, or observing this equation we have common elements in the first two term and the second two term. We can simplify as it is. Here in the first two term common element is m square. So remaining, that is, we can factorize this by taking common elements. Taking m square as common term, remaining element is m minus 1. In these two element common term is 4. Remaining element is m minus 1 equal to 0. Again the common element is m minus 1 and remaining element is m square plus 4 equal to 0. Equating to 0, m minus 1 equal to 0 and m square plus 4 equal to 0. From this we get the first root m is equal to plus 1. Here we have m square plus 4 is equal to 0. Then m square is equal to minus 4 and m is equal to root of minus 4, which is equal to plus or minus 2i. It is a complex element with the real term equal to 0. Therefore, the complete roots are, therefore the roots are 1 plus or minus 2i. Since it is an equation of order 2, we get 3 roots, 1 plus 2i and minus 2i. Here the roots, in the first root it is a real root and second and third root are the complex root. For that we have to write the complementary function using case 1 and case 3. Therefore, yc is equal to, for the real root, c1 e to the power of 1x. Since we have 3 roots, we have to select 3 complementary elements, c1 e to the power of 1x. Next, in the complex element, the real term is 0. We can write this root as 0 plus or minus 2i. We can write the root as 0 plus or minus 2i. The real term is equal to 0. So that can be written as e to the power of 0x. Here we already written c1. That's why c2 into cos 2x plus c3 into sin 2x. c1 e to the power of 1x plus e power of 0x into c2 cos 2x plus c3 sin 3x. So this is the complementary function of the given equation. Next we have to find particular integral. To find particular integral, we have to use the RHS part of the given equation, and the function is sine hyperbolic 2x. We can simplify that as an exponential term, that is e power of 2x minus e to the power of minus 2x divided by 2. So and yp formula is yp is equal to whatever the given phi of x function divided by f of d. Phi of x divided by f of d. Here the value of phi of x is 1 by 2 into e to the power of plus 2x e power of minus 2x whole divided by f of d. Here to simplify this, we have to split the element as e power of 2x divided by f of d minus e power of minus 2x divided by f of d. And we have to carry the procedure for both the elements here, and 1 by 2 is the common term. So then yp is equal to 1 by 2 is the common term here, 1 by 2. First element is e to the power of 2x divided by f of d. What is the value of f of d here? D cube minus d square plus 4d plus 4. This differential operator equation is f of d, that is function of differential operator, d cube minus d square plus 4d plus minus 4. This is the differential operator. This is for the first term, e power of 2x divided by f of d minus e power of minus 2x divided by f of d, that is d cube minus d square plus 4d minus 4. Splitting that function into two elements. Now simplifying this, to find the value of yp, the procedure is we have to replace d by the coefficient of x in the exponential term. Here we have plus 2, here we have minus 2. For that, here replace d by 2, and in this term replace d by minus 2. Replace d by 2, replace d by minus 2. Then yp is equal to 1 by 2 e power of 2x in the numerator, denominator. On substituting d is equal to 2 cube, that is 8, minus 2 square, that is 4, plus 4 into 2. 4 into 2 is 8 minus 4. In the second term, we get e power of minus 2x divided by minus 2 whole cube is minus 8, minus 2 whole square is plus 4, plus into minus we get minus 4, 4 into minus 2, that is minus 8, and again minus 4. So on simplifying this, we get minus 4, that is minus 8. Here we have plus 8. Minus 8 plus 8 get cancelled. We left with 8 in the denominator, which is non-zero element. That means this is the solution of the first term. In the second term, again here also we have minus 8, minus 8, minus 4, minus 4. On simplifying this, we get minus 24. That is also a non-zero element. Therefore, yp is equal to 1 by 2 e power of 2x divided by 8 minus e power of minus 2x divided by minus 24. So on simplifying this denominator, we get minus 24. And now again simplifying this, here minus of minus plus, and multiply this 2 here, we get e power of 2x divided by 2 into 8, 16, minus of minus, that is plus 2 into 24, e power of minus 2x divided by 2 into 24, 48. So this is the value of particular integral. So therefore the final solution is y is equal to yc plus yp, where yc is here, this is the complementary function, c1 e to the power of 1x plus here we have e to the power of 0x. E power of 0 means which is equal to 1. So that's why 1 into c2 cos 2x plus c3 sin 2x. c2 cos 2x, c3 sin 2x. This is the complementary function, plus particular integral value is e power of 2x by 16 plus e power of minus 2x divided by 48. So this is the solution of the given differential equation. Next problem is solve d square y by dx square minus 4y is equal to cos hyperbolic 2x minus 1 plus 3 power of x. So here both the function can be written in the form of exponential term. This cos hyperbolic can be written as e power of ax plus e power of minus ax divided by 2, where a is equal to 2 here. In this one we can write this 3 power x as e power of log 3 into x. So now write the given differential equation. What is given? D square y by dx square minus 4y is equal to cos hyperbolic 2x minus 1 plus 3 to the power of x. This cos hyperbolic function can be written as, this is f of, this differential operator element is d square minus 4 of y is equal to e to the power of 2x minus 1 plus e to the power of minus 2x minus 1 whole divided by 2, and the second term can be written as e to the power of log 3 of x. Here we have three different elements. We have to find particular integral for all the three. Again splitting this, d square minus 4 of y is equal to, first term can be written as e power of 2x minus 1 divided by 2, second term e to the power of, on multiplying this negative sign, minus 2x plus 1 divided by 2 plus e to the power of log 3 of x. So these are the three elements, and this is f of d of y and this is phi of x here. So let us represent this as 1 and this as equation number 2. Now to find the solution of equation number 1, we have to find yc and yp. Yp is based on the RHS function, yc is based on the LHS element. So to find yc, let us write auxiliary equation. What is auxiliary equation here? We have d square minus 4 of y equal to 0. So auxiliary equation is m square minus 4 is equal to 0. We can simplify easily. M square minus 4 equal to 0. Then m square is equal to plus 4. If m square is equal to plus 4, m is equal to root 4. If m is equal to root 4, then that is equal to plus or minus 2. Therefore, two roots are plus 2 and minus 2. Therefore, complementary function yc is equal to, it comes in case 1, c1 e to the power of 2x plus c2 e to the power of minus 2x. First part complementary function, c1 e power of 2x, c2 e power of minus 2x. And next, to find the particular integral of the same, that is to find the value of yp, formula is phi of x divided by f of d. Phi of x divided by f of d, where the phi of x in this is e to the power of 2x minus 1. Here we have e to the power of 2x minus 1 divided by 2. I will write that 2 as 1 by 2 e power of 2x minus 1 divided by f of d. So where f of d is equal to d square minus 4. D square minus 4. Next, the second term plus e power of minus 2x plus 1. Second term is e power of minus 2x plus 1 by 2. Again that by 2 can be written as 1 by 2 into e power of minus 2x plus 1 divided by f of d, that is d square minus 4. And the last term is plus, that is e to the power of log 3 of x divided by d square minus 4. That is the last term. Now applying the procedures, yp is equal to, in the first element we have a is equal to 2, in the second element a is equal to minus 2, in the last element we have a is equal to log 3. So that's why I'll write this 1 by 2 as it is. In the first element replace d by 2, in the second element replace d by minus 2, in the last element replace d by log 3. So d by log 3. So first element is 1 by 2 e to the power of 2x minus 1 divided by, replacing d by 2. So d is equal to 2. 2 square value is 4 minus 4. Second term 1 by 2 e power of minus 2x plus 1 divided by, here we have minus 2 whole square is plus 4. Again we have plus 4 minus 4. And in the last term e to the power of log 3 of x divided by log 3 whole square minus 4. Here, except the last term, in the first two element, denominator value equal to 0. See here, 4 minus 4 equal to 0. Here also 4 minus 4, that is denominator equal to 0. While finding the particular integral, if denominator not equal to 0 like this, then that is the solution. If it is equal to 0, we have to continue further by multiplying the independent variable to the numerator and differentiating the denominator, that differential operator. We have to multiply x to the numerator and we have to differentiate the denominator term. So that is simplifying. Yp is equal to, writing this 1 by 2 as it is, multiplying x e power of 2x minus 1 divided by, what we have here, d square minus 4. Since this term equal to 0, we have to differentiate this operator. What is the differentiation of d square? That is 2d minus differentiation of a constant term is equal to 0. Second term 1 by 2 x, since denominator 0, we have to multiply x to the numerator, e power of minus 2x plus 1. Again differentiation of d square is 2d minus, for a constant term it is equal to 0. And since last term denominator not equal to 0, that is the solution, that remains as it is, e power of log 3x divided by log 3 whole square minus 4. So now simplifying this, after differentiating, again we have to apply the same procedure, replace d by, what is the value of a, that is 2. Replace d by 2, replace d by minus 2, and the solution for this part is completed. Yp is equal to 1 by 2 x into e power of 2x minus 1 divided by 2 into 2. second term 1 by 2 x into e power of minus 2x plus 1 divided by 2 into minus 2, and last term e power of log 3 of x by log 3 whole square minus 4. So here the denominator is not equal to 0. This is equal to 4. This is equal to minus 4. And this solution is already completed. Log 3 whole square minus 4, which is not equal to 0. So that means this is the particular integral solution. But simplifying this, yp is equal to, we have this 1 by 2 in the numerator. Simplifying this, we get 1 into numerator x into e power of 2x minus 1 divided by 2 into 2 into 2, that is 2 cube, which is equal to 8. Second term x into e power of minus 2x plus 1 divided by minus 8 plus e power of log 3 of x divided by log 3 whole square minus 4. So this is the solution of particular integral. Next, to write the solution of the complete problem, therefore solution is y is equal to yc plus yp. Solution is y is equal to yc plus yp, that is, what is the value of yc here? c1 e power of 2x, c2 e power of minus 2x. c1 e power of 2x, c2 e power of minus 2x plus yp value is this complete solution x into e power of minus plus 2x minus 1 by 8. Here we have minus 8 in the denominator. Multiply this, plus into minus, we get minus x into e power of minus 2x plus 1 divided by 8, and the last term here, this 3 power x can be written as e power of log 3 of x. By using this symbol, by using the formula, a power x can be written as a power of log a into x. This can be simplified as a to the power of, this can be written as x into log a. Log a into x, or x into log a. This can be written as a to the power of, e to the power of log a to the power of x. For a log function, x log a is equal to log a power x. That can be written as e power of log a power x, and e log it cancel, we left with a power x. That is, this e power of log 3x can be written as 3 power x, that is 3 to the power x divided by denominator term log 3 whole square minus 4. So this is the solution of the given differential equation. D square y by dx square minus 4y is equal to cos hyperbolic 2x minus 1 plus 3 power of x. After completing problems on exponential term, that is type 1, let us discuss the problems on type 2 phi of x function, that is sin ax or cos ax. As usual, first we have to find complementary function taking LHS part of the given differential equation. To find a particular integral, if the function, that is phi of x equal to sin ax or cos ax, we have to apply this procedure, that is yp is equal to phi of x divided by f of d. So whatever the order of the different denominator term, write it as f of d. Here we have to replace d square by minus a square. We have to replace d square by minus a square, and the value of f of minus a square is not equal to 0. It should be not equal to 0 in the denominator. In case after substituting d square by minus a square and the term not equal to 0, then if d term exists in that equation, if d term exists in the denominator equation, we have to multiply by the conjugate of d. The conjugate of d is, suppose if in the denominator we have 2 plus d, after replacing d square by minus a square, and if it is not equal to 0, if we left with this term 2 plus d, then and the numerator phi of x as it is, then we have to multiply the complete equation by the conjugate of the denominator. Conjugate of the denominator means we have to change the sign of the d element. If it is 2 plus d, we have to multiply by 2 minus d and divide by 2 minus d. We have to multiply, if d term exists, then multiply and divide by its conjugate. Multiply and divide by its conjugate. That is, if it is 2 plus d, then multiply and divide by 2 minus d. If it is 2 minus d, then multiply and divide by 2 plus d. That is, conjugate means change the sign of the d element. After if d term exists, then multiply and dividing by its conjugate. Then again we have to continue the same procedure. Replace d square by minus a square. If it is not equal to 0, then that is the complete solution. If in case d term exists, then we have to apply the same procedure. If the d term doesn't exist, this will be the final solution. In case if f of minus a square is equal to 0, if it is not equal to 0, this is the procedure. Suppose if the denominator is equal to 0, then for yp we have to multiply x in the numerator for the phi of x function, and then we have to differentiate the denominator. We have to apply this procedure only if this term equal to 0. If this term not equal to 0 and d term doesn't exist, this is the final solution. If it is not equal to 0 and d exists, then we have to multiply and divide it by its conjugate. Conjugate means we have to write by changing the sign of the d element. So this is the procedure to find the value of particular integral for trigonometric function. And in this category, the functions are phi of x may be equal to basic trigonometric sine or cos function, or the function may be in the form of sine square ax, cos square ax, or cube of the elements. We have to reduce the given equation to this form. Sine square means we have to write in this form 1 minus cos 2x by 2. Cos square can be written as 1 plus cos 2x by 2. Then we have to split both the element. On splitting this, we have to write in this form. Cos 2x where a is equal to 2. Again cos 2x, a is equal to 2. If the power of the trigonometric function is given, then applying the trigonometric results, we have to reduce to the basic form sin ax and cos ax. So this is a procedure to solve problems on trigonometric functions. Yes, first problem on type 2, that is y double dash minus 4y dash plus 13y is equal to cos 2x, where cos ax is equal to cos 2x and a is equal to 2. To find the solution of this differential equation, here y double dash is nothing but d square y by dx square minus 4 into dy by dx plus 13y is equal to cos 2x. This equation can also be written as d square minus 4d plus 13 of y is equal to cos 2x, and this element is function of a differential operator d of y is equal to phi of x is equal to cos 2x. To find the solution of this equation, first we have to find auxiliary equation. Auxiliary equation is m square minus 4m plus 13 equal to 0, and obtained equation is a quadratic equation. If it is possible, we have to factorize this, otherwise we have to apply formula to find the roots of the equation. Here 1 into 13 We have 13 as a factor. We have to select two numbers. On multiplying, we should get 13. But for this, factorization is not possible. Hence, applying the result, a is equal to 1 here. I am writing the coefficient of this quadratic equation. B is equal to -4. C is equal to 13. Finding the root, m is equal to, formula is minus b plus or minus b square minus 4ac divided by 2 times of a. Then m is equal to minus, b value is -4 here, plus or minus b square value is -4 whole square, that is 16, minus 4 into 1 into 13 divided by 2 times of a value is 1. Simplifying again, m is equal to minus of -4 plus 4 plus or minus, we get 16 minus 52 here. 16 minus 52 is minus 36 divided by 2. Simplifying again, 4 plus or minus root 36 is equal to 6, and root of -1, it is a complex term, that is I, that is 6i divided by 2. Again simplifying this, 4 by 2 is 2, 6 by 2 is 3, 2 plus or minus 3i. So 2 plus or minus 3i is the obtained root. Roots are 2 plus or minus 3i. We have two roots here, 2 plus 3i and 2 minus 3i. Therefore, yc is equal to e to the power of real term of the obtained complex element is 2, e to the power of 2x into c1 cos 3x plus c2 sin 3x. c1 cos 3x plus c2 sin 3x is the complementary function. After finding complementary function, next to find particular integral for the given phi of x. To find yp, that is, formula is yp is equal to phi of x divided by f of t. In the given problem, the value of phi of x is equal to cos 2x and the value of f of d is equal to d square minus 4d plus 13. F of d value is d square minus 4d plus 13. So according to type 2, if phi of x is a trigonometric function, we have to replace d square by minus the coefficient of that variable, that is minus 2 square, which is equal to minus 4. So therefore yp is equal to cos 2x divided by, on replacing d square by minus 4 minus 4d plus 13. On simplifying this, we get cos 2x divided by minus 4 plus 13 is plus 9 minus 4d. On replacing d square by, that is minus a square, which is in the given problem minus 2, on replacing that, if we get d element, if d term exists, then we have to multiply by its conjugate. Conjugate of 9 minus 4d is 9 plus 4d divided by 9 plus 4d. On simplifying this again, yp is equal to 9 into cos 2x, that is 9 cos 2x plus 4 into d of cos 2x, that is nothing but differentiation of cos 2x, which is differentiation of cos is minus sin 2x into differentiation of 2x is 2, minus 2 sin 2x divided by, observe the denominator, we have 9 minus 4d into 9 plus 4d, that is a minus b into a plus b, which is equal to a square minus b square. A square is 81, that is 9 square, minus b value is 4 square, that is 16d square. After simplifying the denominator, here d square element exists. Again replace d square by that coefficient constant, that is minus 2 square. On simplifying, yp is equal to 9 cos 2x minus 8 sin 2x divided by 81 minus 16 into d square. Again d square value is minus 4. Simplifying this, we get 9 cos 2x minus 8 sin 2x divided by 81 minus of minus plus 16 into 4, 64. On simplifying this obtained value, the value of yp is equal to 9 cos 2x minus 8 sin 2x. In the denominator we have 81 plus 64, which is equal to 145. This is the value of particular integral for the given problem. And the complementary function is e power of 2x c1 cos 3x plus c2 sin 3x, and particular integral is 9 cos 2x minus 8 sin 2x divided by 145. Hence the complete solution of the given differential equation is y is equal to yc plus yp. Y is equal to, where the value of yc is e power of 2x c1 cos 3x plus c2 sin 3x plus 9 cos 2x, that is yp value 9 cos 2x minus 8 sin 2x divided by 145. So this is the complete solution of the given problem. Next, the second problem in type 2, solve d square plus 4 of y is equal to sin square x. In the previous problem, we have cos 2x with a trigonometric function with power 1. We have the trigonometric function power 2 in the second problem. So let us solve this. So given d square plus 4 of y is equal to sin square x. To find a particular integral of sin square x, first we have to reduce this sin square x to the basic form. We have the result that 1 minus sin square x is equal to 1 minus cos 2x divided by 2. 1 minus cos 2x divided by 2, or this can be written as this d square plus 4 is a function of a differential operator of y is equal to 1 by 2 minus cos 2x by 2. We are solving problems in type 2 category, that means a trigonometric function. Here cos ax, where a is equal to 2. If it is a constant term, we can write this one is also in the trigonometric form as 1 can be written as cos 0x. The value of cos 0 is equal to 1. So 1 can be written as cos 0x. Here a is equal to 0. Here a is equal to 2. Where this is the given phi of x function here. First find the complementary function. For that, auxiliary equation is m square plus 4 equal to 0. For this, m square is equal to minus 4. M is equal to root of minus 4, which is equal to plus or minus 2i. M square is equal to minus 4, root of 4 is 2, root of minus 1 is plus or minus I. It is a complex root. For a complex root, complementary function is yc is equal to this. In this complex root, the real part is 0 plus or minus 2i. 0 plus or minus 2i. For that, complementary function is e power of the real term, that is e power of 0x plus into c1 cos 2x plus c2 into sin 2x is the complementary function. E power of 0x, c1 cos 2x plus c2 sin 2x is the complementary function. Next, to find particular integral, yp is equal to phi of x divided by f of d. Here the phi of x value is cos 0x by 2, and f of d, we have f of d is equal to d square plus 4 minus cos 2x divided by 2 into d square plus 4. Here by 2 is common in both the element, hence yp is equal to 1 over 2 cos 0x by d square plus 4 minus cos 2x divided by d square plus 4. Here in the first term the constant term is 0, a is equal to 0, hence replace d square by a. Replace d square by a value is 0 in the first term, in the second term d square by minus 2 square. For 0 we can it will be same on substituting both negative and positive term, hence d square by 0 in the first term, d square by minus 2 square in the second term. Hence the yp value is 1 by 2 cos 0x value now it can be written as 1 divided by d square is equal to 0 plus 4 minus cos 2x divided by, on replacing d square by minus 4 we get minus 4 plus 4, and the value of minus 4 plus 4 is 0, that is the denominator of the second term is equal to 0. That means we have to continue further. Yp is equal to 1 by 2 into 1 by 4. Since the denominator value is 0 in the second term, we have to continue with that part only and writing the first element as it is. If denominator term equal to 0, then we have to multiply x to the numerator. As I explained earlier, multiply x to the numerator, that is x into cos 2x, and differentiate the denominator. What we have in the denominator? D square plus 4. On differentiating this, we get 2d. On differentiating d square, we get 2d plus differentiation of 4, that is a constant term which is equal to 0. 2d plus 0, hence we get 1 by 2 into 1 by 4 minus x cos 2x divided by 2d. I am substituting d square is equal to 0 in the first term, we have 0 plus 4. For the second term we get minus 4 plus 4 as denominator 0. Since the denominator is 0 in the second term, we have to continue the further procedure for the second term only. Denominator is equal to 0, hence in the numerator term we have to multiply x for the numerator and we have to differentiate the denominator as I already explained earlier. So multiply x to the numerator and differentiate the denominator term minus x cos 2x divided by 2d. In the next step, yp is equal to 1 by 2 divided by 1 by 4. Since d term exists here, we have to multiply and divide by its conjugate, that is minus 2d, or in this particular problem we can solve in the simple way, that is x cos 2x divided by 2d, that is 1 by d we have here. 1 by d is nothing but reciprocal of the derivative, which is an integral. That means writing minus x by 2 as it is, cos 2x by d is nothing but integration of cos 2x, that is cos 2x divided by d is nothing but integration of cos 2x. On integrating, integration of cos 2x is sin 2x divided by 2. Integration of sin 2x is cos 2x is sin 2x divided by 2. Therefore, yp is equal to multiplying 1 by 2 inside, 1 by 8 minus 2 into 2 4, 4 to the 8 minus x sin 2x divided by 8. So this is the solution of particular integral. 1 by 8 minus x sin 2x by 8. Therefore complete solution is y is equal to yc plus yp, and y is equal to, what is the value of yc here? Here we have e power of 0x, which is equal to 1, remaining c1 cos 2x plus c2 into sin 2x, c1 cos 2x plus c2 into sin 2x, plus particular integral value is 1 by 8 minus x sin 2x by 8. 1 by 8 minus x sin 2x by 8 is the complete solution of the given differential equation.